Okay, so hello friends. This is another new lecture, and in this lecture, I will discuss about the carrier concentration for electrons in conduction band. So we will consider here that in intrinsic type semiconductors are, as we know, classified into extrinsic and intrinsic semiconductor, and here I will consider that intrinsic semiconductor, where on the basis of that band theory we will have that valence band and conduction band. So in this lecture I will derive that carrier concentration for electrons in conduction band only. So before this derivation, we should know some terms which I am going to use here, and the first one is that N, E, and this is obviously N is the number, and here we are just talking about that carrier concentration or the carrier density. So obviously we will talk about the numbers per unit volume. So here this Ne is actually the number of, if we are talking about electrons, then number of electrons per unit volume in a specific given energy E. So this is the function of energy E. So this is the total number of electrons per unit volume in this given energy E. Second, we will use this if this Ne multiplied by dE means we are confining that number of electron in a very small energy gap, then this will be the number of electrons per unit volume in the energy range E and E plus D. So if we have this conduction band and valence band, and this is this energy gap is E, and this is valence band, and this is the conduction band. In this conduction band there are so many energy levels, and we are talking about a specific energy E, and here in this energy level, if we want to calculate the total number of electrons per unit volume, then this is represented by Ne, and if we take another energy level here, this is E plus dE, and we consider this energy gap as equal to dE, then the number of electrons per unit volume in this energy gap del E, this is represented by NEDE. And obviously there will be several lines, number of states here, and this is corresponding to valence band, and this will be the conduction band. We will concentrate in this band only. Now the third term we are going to use here, this is that GE, and I think in previous level of lecture I have represented this by GE. This is the density of state. So these lines, the empty lines, are that density of states. These are actually the available states per unit volume, again per unit volume, to be occupied by electrons in energy E. So at a particular energy value E, these states, number of states, are known as density of states, and if it is multiplied by dE, then the same density of states, that available states per unit volume in the energy range E and E plus dE. And that fifth one is that Fe. This is the Fermi-Dirac Fermi-Dirac function. And this Fermi-Dirac function actually gives the probability. This gives the probability of occupancy of electron. Occupancy of electron in energy E at temperature T. So at particular temperature T, at a specific energy E, the probability of that existence of electron or occupancy of that electron is given by this Fermi-Dirac distribution function. So we will use these terms to find out that carrier concentration and carrier density. Okay, so let's start with that derivation part. So here that carrier density carrier density is represented by Nc, and it is defined as equal to NEDE. This is for that specific energy gap, and if you want to calculate within this complete conduction band, so the carrier density in the conduction band this is represented by Nc, and this is equivalent to NEDE from integration of the NEDE. In between this EC, the lower energy value here is EC, and this upper energy level may be up to the infinite. So the integration will be in between that lower energy value EC and the upper energy value infinite. But this NE, this is that total number of occupied electrons in this energy range, and we are just integrating to get that carrier density, means number of electrons per unit volume for this complete energy range. So here is NEDE. This is defined as equal to the multiplication of density of state in this energy range, and with this Fermi-Dirac distribution function with this. How this is? This is that total number of available energy states, energy levels to be occupied by electrons, and this gives the probability of occupancy of that electron at that particular energy level. So the multiplication of these two, this gives that number of electrons per unit volume in that small energy range GE, and when we integrate this in this range, then we can get this NC. So this is a simple definition of that carrier density, and now we will calculate further. And here where this density of state dE, previously we have derived this density of state dE, it is equal to 1 upon 2 pi square 2m by h cross square 3 by 2 and root of E. So this is that density of state, that is 1 upon 2 pi square 2m h cross square 3 by 2 root of E. And for an electron, for electrons in conduction band, we will have this dE, it is equivalent to 1 upon 2 pi square, this is 2me star, this is me star, this is the effective mass of electron by 8 cross square 3 by 2 root, and here that energy E will be replaced by E minus EC, where EC is the lower energy value of this conduction band. So this is that density of state, and here I should write Me star, this is effective mass of electrons. And this is the first term. Now the second term Fe, the Fermi-Dirac distribution function, this is equal to 1 upon 1 plus exponential of E minus EF by kT. Its significance at various temperatures we have studied in our previous lecture. So this is that Fermi Dirac distribution function, and here we will use a simple approximation like that. If E minus EF is much greater than kT, then this implies exponential of E minus EF by kT, this will be much greater than 1. So this exponential function dominates this value 1. So Fe can be written as equivalent to approximately equal to exponential of minus E minus EF. So this is dominant, so this will be transferred to numerator and with minus sign. So now I will put the value of dE and the value of Fe here in this equation, and that Nc will be now so this is equal to Ec to infinite density of the state multiplied by F this and dE, and by putting that approximations I will have this Ec to infinite, dE is this is that dE 1 upon 2 pi square 2 me star by h cross square 3 by 2 root of E minus Ec, and that Fe with this approximation, that is multiplied by exponential of E minus EF by kT and multiplied by this dE, and that integration is limited to from Ec, that lower energy value Ec, to infinite. Now this is the constant, so we can replace this as equal to A and Ec to infinite. In the simple mathematics we will perform here, and this is exponential of E minus EF by kT integration of E minus Ec multiplied by dE. Now let us see what is the difference between these two terms. Here this is in between E minus EF to the Fermi energy level, and here this is E minus Ec. So here this is that Fermi energy level for that pure semiconductor. So we have to convert this term with this Ec. So let us make a substitution like that. So this is Ec to infinite exponential of, now let us see what I am trying to do here. This is E minus Ec, obviously with minus sign here, so we will take with a plus sign again. So Ec minus Ec plus minus EF by kT with integration of that E minus EF and the dE. Now we can convert this into two parts. One is related to this and another is related to this. And Ec, this is the constant, this is also the constant, so one constant can be taken out from this integration side. So we will have so Nc, it is equivalent to a constant A multiplied by the exponential of minus Ec minus EF by kT with the integration of minus Ec to infinite, and that another term is exponential of minus E minus this Ec by kT multiplied by E minus Ec multiplied by E. So this is one integration term, and I will use substitution. So this is a simple integration term, and I will use the substitution method to solve it. So let us have, let E minus Ec by kT this is taken as equivalent to x, so this is taken as equivalent to x. So this implies dE it is equal to, this will be transferred to here, so kt multiplied by dx, and also this limit will be changed. So here if we take this E is equivalent to EC, and that limit is converting in terms of x, so if this E tends to EC, so E tends to EC, then this implies x is equivalent to 0, and if this E, that upper limit, it tends to infinite, then this implies x tends to infinite. So again, let's see, when we are taking this energy E is equivalent to EC, that E is equal to EC, then this x is equivalent to 0. When we put this E is equivalent to infinite, then obviously x tends to infinite, so limit will be changed to 0 to infinite. And now let us put all these terms here. So this NC is equivalent to A exponential of EC minus EF by KT, and now let us put that integration value from 0 to limit from 0 to infinite, and this will be e to the power x minus x, and here this is root of x dx. So this is a simple integration term, and here we will use a mathematical function that is known as the gamma function to solve this. So from the definition of gamma function, actually students should know this this mathematics of related to gamma function, and if they are not familiar with these terms, then they have to memorize this. So this gamma function is defined as gamma n, it is equivalent to integration in the limit 0 to infinite e to the power minus x, e to the power minus x, and x to the power n minus 1 dx. This is the definition. Here let us compare this with this. So here e to the power x is here, e to the power minus x is here, and here in place of this root of x we have this n minus x. So by comparing these two, so here n will be equal to 3 by 2, n minus 1 is equal to half, so n is equal to 3 by 2. So by putting this n is equal to 3 by 2, we will have by using this, we will have this NC, it is equal to A exponential of minus EC minus EF by KT multiplied by gamma 3 by 2, n is equal to 3 by 2. So since this gamma function 3 by 2 is equal to root 5 by 2, so students should also know the value of this. And the final term we will have for this NC till now will be equal to, so this NC till now is equal to A exponential of EC minus EF by KT multiplied by root of 5 by 2. Now we will rearrange that this function by putting the value of A here. This NC is equal to this A, it is equal to 1 upon 2 pi square 2 me star by h cross square 3 by 2, and exponential of minus EC minus EF by KT multiplied by root of 5 by 2. So this is the term, and one can write this as answer, but let me further modify this term by substituting this h cross. Since h cross is equal to h upon 2 pi, so this NC can be also written as equal to 1 upon 2 pi square. Now 2 me star, and I think I have forgotten that term KT 3 by 2. That should be 1 KT 3 by 2, because when we substitute that E minus EF by KT is equal to X, then there will be one additional KT term is there. So this KT 3 by 2 is here. So here that KT 3 by 2. So this KT can be taken inside this KT, because this power is also 3 by 2. This is also 3 by 2. So and H cross can be written as equivalent to H upon 2 pi by square and 3 by 2 exponential of EC minus EF by KT and multiplied by this root pi by 2. So I am just taking out all the pi terms out of this bracket, and we will have this NC, it is equal to 1 upon 2 pi square multiplied by 2 me kt by, this is h square now, and this is 2 pi square, and this is 3 by 2. So this will be 2 pi thrice, and this pi term is here, root of pi by 2 exponential of minus EC minus EF by KT. So here this is pi square, here this is pi cube, so and this is 2 cube, and there is another 2 here, this, so one will have this is 4, this is 8, so this is 2 times, and now pi square, this pi square is cancelled, 1 pi will remain here, and there is the root of pi, so that will be pi 3 by 2. So this is 2 pi MEKT by h square 3 by 2 exponential of minus EC minus EF by KT. So calculation is not much complicated if just simple mathematical terms are used, and one can easily convert all these parameters in this term, and this is all these parameters are constant. This 2 pi me, that is specific mass of that electron, K Boltzmann constant, is the temperature. So for any specific temperature, so T can be taken out, this is not constant, H cross. So this is equal to NC exponential of EC minus EF by KT. So this is NC, where NC, capital N, C, this is equal to 2 me star multiplied by KT by h square by 3 2. This is known as specific density of states. So this NC, this is the derivation for the carrier concentration. This is the derivation for the carrier concentration in conduction band, and this is the function of, if this NC is the function of temperature, so at different temperatures the carrier concentration may be different, but for a specific temperature this can be taken as a constant. So in the next lecture we will derive that carrier concentration, and there we will consider the hole, and the holes are inside the valence band. So in the next calculation we will consider that. So wait for that. Thank you all.